is equal to x squared plus y squared. And also note, remember, z is just equal to z. Okay. All right, so let's kind of look at our bounds for a second. Let me go and erase this. How would this change our bounds if we go to cylindrical coordinates? Okay. Well, z, remember, stays as z. So in cylindrical, not much is changing with z except for this part right here. Okay, because when we change to cylindrical coordinates, we shouldn't see an x and a y anymore, right? But we know, remember, r squared is equal to x squared plus y squared. So that means that minus r squared is equal to minus x squared minus y squared. So our bounds for z become 16 minus r squared. Okay. Now, what about r and theta? Okay, well, remember when we smashed our bowl into the xy plane, we got a circle of radius 4, right? Okay, so how do you get the full circle of radius 4? Well, r has to go from 0, okay, the origin, all the way to 4, so that we get everything in between. And then to get the full revolution of the circle, theta has to go from 0 to 2 pi. Okay, so there would be our bounds in cylindrical coordinates. Okay, and then of course we have to, notice in our function here, we have to also change that, but we'll do that in the next screen. Okay, so then our triple integral of the function 8 plus x plus y dv is equal to, so we're going to go ahead and jump right to cylindrical coordinates, integral from 0 to 2 pi, so that was theta, so I'll put that at the very end, d theta. Actually, I'm probably going to need some more room. Please erase. There we go. Okay. And then r was going from 0 to 4, and then z was going from 0 to 16 minus r squared. Okay, so 8 plus, notice I'm using a parenthesis for a very, very specific reason. We'll see that in a second. X is our cosine of theta, plus y is our sine of theta. And then remember, if you convert to cylindrical coordinates like we did with polar coordinates, you have to multiply by a factor of r. Okay, so this will be dz, let's see, our middle integral is r, d theta. Okay. All right, squeeze it in there. All right, so now let's go ahead and integrate this like we normally would. Let's see, let's go ahead and distribute r first. Yeah, let's go ahead and distribute r. So if we distribute r, we're going to get, oh, do I want to do that? Yeah, let's go ahead and do that. I didn't know I can zoom in like that. That's awesome. All right, so this is equal. Can I write though? Please? Ah, there we go. PowerPoint is very strange sometimes, everyone. All right, so this triple integral, 2 pi, 0, 4, 0, 16 minus r squared, 0. So I'm going to go ahead and distribute r. Okay, dz, dr, d theta. Oops. Okay. So now, if we integrate with respect to z, notice that this would technically be a constant, right? So if we integrate with respect to z, all we're going to get is, oh, PowerPoint. Why are you doing that to me? Okay, this is equal to integral 2 pi, 0, integral 0, 4. All right, so we're going to get 8r plus r squared cosine of theta plus r squared sine of theta times z, evaluated at 16 minus r squared and 0. Okay. Oops, and let's not forget the other differentials, dr, d theta. Go back. Okay, So if we evaluate this at 16 minus r squared, if we evaluate z at these two bounds, all we're going to get is, I'm going to go ahead and replace it so I'm saving a little bit of space and time. I'm just going to get this whole thing times 16 minus r squared. Okay. So now let's see. Let's go ahead and integrate with respect to, r. We'll just go ahead and do it straight up like we have here. So let's go ahead and distribute the 16 minus r squared. So we're going to get, let's see, we'll get, 8 times 16 is going to be 80 plus 48, so 128. R minus 8r cubed plus, actually, no. I take this back. Taking it back, everyone. Do I really want to do that? Because we're going to get a lot of terms to calculate. Notice, by the way, integrating triple integrals can be done in a lot of different ways, and because there's a lot of work, I'm trying to be as clever as possible. You know what we're going to do? Since this is a double integral, technically over, we have constant bounds here. Let's go ahead and change the order of integration, because it would be easier to integrate with respect to theta rather than r. So let's go ahead and change the bounds like this. And let's make sure we change our differentials too. Okay. And notice again, because we're dealing with constants there, I can change that and I'm not hurting anything. Now, if we had other functions here in our integrals, we couldn't do that as easily. Now, the reason why I'm doing this is I can first factor out the 16 minus r squared, because remember, we're integrating with respect to theta now. Let me pull that out. Okay, and then now we're integrating, I think, something a little bit slightly nicer there. So this is going to give us the integral from 0 to 4, 16 minus r squared, times, okay, now if we integrate with respect to theta, we'll get 8r theta plus integral of cosine is sine minus integral of sine is cosine. Okay, evaluated at 2 pi and 0. Let's not forget our last differential there. So this becomes integral 0 to 4 of 16 minus r squared times, all right, so if we plug 2 pi into this, we'll get 16 pi r, okay, plus 0 minus r squared. Okay, minus, if we plug 0 into this whole thing, okay, we're going to get 0 from this part, we'll get 0 from this part, and then from this part we'll get another minus r squared. Oh, you guys, look how much nicer this is going to be. Oh, no, don't look. PowerPoint. Why you be like that? Okay. So the reason why I like this is notice that the r squareds now go away. Oh, you guys, this is much better. Okay. So let me go ahead. Let's go to the next slide, and I'll try to remember what we have here. So we'll have the integral from 0 to 4. We still had that 16 minus r squared, and the only thing that survived was a 16 pi r. Okay. So now let's go ahead and integrate this, and oh yeah, this is much better. So that's one of the things you want to keep in mind when you're doing these more complicated integrals is possibly switching the order of integration, because it could save you a lot of strife. Okay, so this will be 16 squared, which I don't know off the top of my head, pi r minus 16 pi r cubed dr. And so now let's integrate. So we'll get 16 squared pi r squared over 2 minus, let's see, it'll be 4 pi r to the 4th evaluated at 4 and 0. Okay, so this will be, let's see, if we plug in 4, we'll get, let's see, 16, so it'll be 16 cubed pi over 2, minus we plug 4 into this. It'll be 4 pi to the 5th. I'm sorry, 4 to the 5th pi. Okay, and if we plug in 0, we'll get 0. And let me go ahead and pull open a calculator. What is 16 cubed divided by 2 minus 4 to the 5th? 1024. So this is going to give us, in the end, 1024 pi. Huzzah, which I know is the correct answer because I got this out of my old textbook, my old multivariable textbook. Okay. So again, what I want to stress here when you're doing integrals and cylindrical coordinates, take your time and really think about your integration. Don't just integrate straight up. Remember how we changed directions a little bit because it made our lives easier. Think about it. Because triple integrals are going to take a lot longer than single integrals did and more time than double integrals did.